In this video you will learn how to calculate the Coulomb force between 2 point charges which are positioned somewhere in a vacuum. And since the Coulomb force is the primary energy supplier in most electrical engineering applications, a basic understanding of how this works is very important, hence this exercise. And in addition to computing the force using the electric field, we will also calculate how much mass we can accelerate with the charges in the example to arrive at the same values as, for example, a Tesla Model 3 electric vehicle. My name is Andreas from The Fearless Engineer, and here we go. Now, before we dive into this example here, let's briefly talk about the motivation behind this exercise. Now, the Coulomb force, which we have previously talked about, is responsible for the movement of charge carriers through a circuit, for example, a copper cable or a PCB which conveys electricity to a resistor or to an integrated circuit. And therefore, the Coulomb force is the basic mechanism, the energy supplier in electronics and electrical engineering. And this is why in this task we will take a closer look at how this force actually works. In a very simple example, we will look at the force between only two charged particles. And the approach is as follows. In the first step, we will calculate the electric field of the first charge at the position of the second charge. Then we will multiply the resulting field by the magnitude of the second charge. And as a bonus chapter, so to speak, as a bonus part, we will put the result which we derive from step number 2 in relation to something that we can relate to. In our case, the forces acting on a Tesla Model 3 electric vehicle. Now let's start with the first step. First, we will calculate the electric field of the first charge at the position of the second charge. So we have a charge Q1, which has a magnitude of 10 microcoulombs with a negative sign, and we will compute the electric field at the position of the second charge, which is 5 centimeters away. And we can easily do this by applying the equation from the last video, which consists of dividing the magnitude of the charge Q1 by the surface area of the enclosing sphere around the first charge in a distance of R12. And we multiply it, we assume everything is positioned in a vacuum. We multiply it by the permittivity of the vacuum, which is at this value here. And if we just run the numbers inside everything, we arrive at a result of minus 3.595 times 10 to the power of 7 volts per meter. And the unit volt, as before, is something which we have not yet introduced, the concept of voltage, but nonetheless we can arrive at a field strength at a certain position in space caused by a charge Q1. And in this simulation here you can see the effects of placing a charge in space. It's only a single charge, it's a negative charge, just as the one which we have used in our calculations. It's the charge Q1. And you can see that the strength of the electric field decreases quadratically with distance. And if the sign of the field strength is negative, you can see that E points towards the causing charge, towards the charge causing the electric field. So in case of a positive charge, the arrows would be pointing outwards, but in our case, the arrows are pointing inwards towards the charge. And in the second step, we now want to compute the force exerted onto the second charge by the electric field of the first charge. So we now already know this field strength at the position of the second charge. We now take a look at the magnitude of the charge, which is 7 microcoulombs, but with a positive sign. And in order to arrive at the force acting on the second charge, we only need to multiply the magnitude of the charge with the electric field of the first charge at the position of the second charge, which has been done here. And if you run the numbers, you arrive at 252 newtons, which is actually quite a lot of force, but bear in mind that it's only acting over a distance of 5 centimeters here. But nonetheless, 252 newton is no negligible force, and actually you can do quite a lot with this amount of force. Before we compare it to the Tesla, let's briefly take a look at the distribution of the electric field in space when we position charges in space. And on the left-hand side, you can see a cluster of negative charges. On the right-hand side, a cluster of positive charges. And you can see how the electric field propagates through space. And we have talked about the symmetry of the force equation before. the negative charges on the left, they exert a force on the positive charges on the right, but this cluster of positive charges also exerts a force which is symmetrical onto the negative forces on the left, and you can see the two force vectors here. So from left to right we have a negative force of minus 252 Newton, and from right to left we have a positive force of the same magnitude, and these two forces obviously cancel each other out because the clusters are stationary in space. And now lastly, let's put the result which we just arrived at in relation to something that shows us the actual magnitude of the force. And in order to do so, let's employ a Tesla Model 3, and we can look up from the datasheet that this car accelerates from 0 to 100 kilometers per hour in only 3 seconds, and it weighs about 1.7 metric tons. And we can now use a simple motion equation, which is the velocity equals the product of acceleration times time. And we can, by using this equation, compute from the values given here that the acceleration of the Tesla, when it really speeds up from 0 to 100, is around 9.27 meters per squared second. And bear in mind that this is very close to the gravitational pull of the Earth, which is quite a lot. And now the question is, to exert a charged, or to accelerate a charged body with the force F12 from the example identical to the Tesla, we can now compute that the body must have a weight of this magnitude here. So we take the force from the previous example, 252 newtons, we divide it by the acceleration of the Tesla, which are these two numbers here. And this result here, 27.21 kilograms, tells us that by exploiting the force between the two charge clusters from the previous example, or from this example here, we can accelerate a mass of 27 kilograms in the same manner that the Tesla accelerates its 1.7 tons. But bear in mind again that we only have this force available over a distance of only 5 centimeters. But just to relate this to something tangible, you can now easily compare the 27 kilograms with the 1.7 metric tons of the Tesla to get a feel for the forces at play here inside the Tesla as well as between these two charge clusters in space. For now, that's all. I hope you enjoyed the video. If you have any questions, please do not hesitate to drop me a question down below in the comments. I wish you a nice day. See you next time here on The Fearless Engineer.